Okay. So what I'm going to suggest that we do is, I know that it's got this expression for the acceleration, but I
Mhm.
would suggest that we do this problem and ignore this one until the end, because getting this exact expression is kind of like, I think of it as not useful in all cases. So
Okay.
um, let me see. I really wish I could. So we're definitely going to, we are going to get an expression for the acceleration, but my claim would be that we really don't need to get this particular one. It's
Okay.
all the remainder of the problem. Except, except that, right. There we go. So just I would suggest that we don't even start out worrying about that yet.
Sounds good.
Okay. Okay. All right. So I'll hand this over. I'll hand this over to you guys. Um, and I would suggest first drawing a picture so that we can just think about what the situation is.
So
Uh,
what
yeah.
I was kind of, so what I kind of imagined was something like a wire like that, uh, and then you have kind of a, maybe I need to make that bigger. And then you have, it would be like a negative and a positive charge, or it basically be a dipole.
Yeah, okay. Let's
Right.
let's actually so okay, this looks exactly like the right setup to me. Let's talk about is the wire positively charged or okay, positively charged in this case. Great.
Yes.
And so originally our carbon, our coal dust, does it have a net charge or no?
I don't believe so because it's,
Carbon's neutral.
yeah, neutral.
Yeah. Okay, great. Great. Okay. And that's consistent. And actually, this is a really minor point, but when you have positive charges, they're going to distribute themselves all around the wire. So actually, the most accurate thing to do is to draw like positives on both sides. Yeah. I'm sorry.
Oh, you're fine.
Uh, okay, fantastic. All right. So then, given that this wire is positive, can you tell me why that dipole? Like, why not draw the plus on the left and the minus on the right?
Because the negative and positive are attracted to each other. So then the positives move away from the positive charge and the negatives move towards it.
Fantastic. Okay, that sounds perfect to me. Okay, and Michael Evanson, does this kind of match your picture of this as well?
Mm-hmm.
Okay.
Because
Okay, great.
positive goes with the flow.
Yeah, it's going to get pushed away by the electric field.
Mm-hmm.
Yeah. Okay, and so now they're asking us to calculate an acceleration. So maybe my first question is, why wouldn't this acceleration be zero?
Because the coal is moving towards basically like the force the from the positive and negative being attracted. Correct. The force of the
Okay.
positive charge acting on the negative charge and vice versa.
Which charge do you mean here? So the force of the
The wire where it's positive,
okay.
attracting the negative charge from the coal.
Okay. I totally agree. But I would also say that the positive charge on the wire is also going to push away the positive charge in the coal.
Would it not be further away though? So it's going to have a smaller
Ah,
effect on it.
okay. What do you guys think, Michael Evanson? Does that
I think that's in line with our fish example, why the further point of measurement got less of one of the other fields given its position.
Yeah. Yeah, I would agree. Right. So in general, so there's only one, right? So certainly for a single point charge, the larger the distance, the smaller the electric field. It's a 1/r² dependence. Um, Now here you have a bunch of point charges to make up a wire. Uh, but a wire also has that same property that the further away you are, the smaller the electric field. In the case of these multiple charges like this in a line, you're going to get a 1/r dependence instead of a 1/r² dependence for the electric field, for the net electric field.
Oh yeah.
Yeah, but I agree. I think it still has exactly that property that you're describing. So, okay, right. So the negative and the positive are very close. So that difference is really small. But it's there, and we can calculate it. But I think I agree with you guys that that's exactly the situation. So the negative part of the dipole is going to get pulled towards the wire, and the positive part of the dipole is going to get pushed away towards the wire from the wire just a little less. And so the net force on this thing is going to end up being in which direction?
To the left.
Yeah.
Yeah.
Agreed.
Okay. Great. So we're here to calculate that small number of, that difference in forces.
Mhm.
Okay. All right. I'm in. I'm sold. This is the situation. So how do we start writing down? Yeah. How do we solve for the acceleration?
Actually, could I ask a question?
Yes, please.
So, I was wondering. So, how do you know like that that negative and that positive charge are equal in magnitude? Because like you were asking like for the acceleration, why one accelerates but one the other one doesn't. I was wondering if maybe the charge, like if the charge aren't the same, like it could not accelerate, but if they are, then it would. But how do we know the charge is the same? I don't
So
know
I
if
think
that makes sense.
yeah. Do you guys have any ideas, Michael and TJ?
It's because it's neutral,
Yeah, that's
and
what I was
so
thinking.
when the charge in the wire induces the dipole in the carbon atom, it creates an equal and opposite tug on both sides.
Does that convincing, Rudra?
Yeah. So I think. Yeah. So the more I think about it, I'm thinking that with that wire, that wire is going to pull those, it pull that electron density towards to the, what is it called, the left. And I think the more electrons that go to the left, the more positively charged the other side becomes. Yeah, that makes sense. It would be the same.
Yeah.
Yeah, no, you're right.
Yeah. I think that's exactly right. Right. The fact that the thing is net neutral, it means that whatever you subtract from one end, it's stuck there as positive.
Gotcha.
But I do agree, right? If there were a difference in charge distribution, then you could have, more positive charge canceling out the difference in the electric field that contributes to the force. Okay. All right. So I think we're all agreed that whatever the negative charge is, it's exactly equal and opposite the positive charge. And I think that we're also all agreed that the net force is going to be small, but it's going to net be in the left direction. And so maybe my question is, how do we start solving for the acceleration? What are your guys' thoughts on that?
Well, so obviously, I kind of where I started was the basic, excuse me, force equals ma,
Great.
and then F equals Q QE, correct?
Yes.
So then we would be looking for MA equals QE, and then A equals.
Oh, sorry. Hold on 1 second. Let me get your. Oh, my computer is so slow. I'm sorry. Oh no. There we go. Yes. Agreed. Okay. So I think the only thing that I would say here is that, yeah, so this is exactly, I think this is exactly right. The only thing that I would say is that we probably, the F equals QE, here we really have a system that's like a coupled two-body system, right? So really with the F equals QE, we really have F equals negative QE minus plus QE plus. Right? So each one of those parts of the dipole has a different force on them.
Gotcha. So okay, so it'd be QE. Oop. And then plus the. That's what.
Yeah.
Is that what you're saying?
And yeah, and the QE minus is going to be negative QE minus because that one is negative Q and the other one is positive Q.
Oh, okay.
Yeah. Yes. Okay. And so then that's going to change your MA equals acceleration and your acceleration equation accordingly.
I'll just do this.
Fantastic. Okay. Now, if I had my way, this is the kind of expression that they would ask you for in this problem. And of course it's not, but so what we're going to need to do is a couple things. And the first thing we're going to need to do is they don't tell you specifically what E minus and E plus is. So in terms of actually getting a number for the acceleration, that strikes me as the first task. But I'll ask you guys, right? So this is the acceleration. So what do we know and what don't we know? That's kind of always the foundational question whenever we have our expression.
So we know the distance from the wire to, I believe when I asked you the other day, we said that measurement was to the center. You can assume it's to the center of the.
Yeah, that's what I was suggesting. Yeah.
That is D. So it's 0.012 meters.
Great.
And then we also know the length of the wire, which is L, I believe. Yes. Which is 0.7 meters.
Excellent.
We also know the charge of the wire, which is 0.7 to the negative 7. Wait, nope, that's not wrong. And then we also.
What are the units on that charge?
Oh, no, I missed that.
Great.
And then we also know the polarizability, which is
we do.
alpha. I believe that's.
I think the units on that aren't quite right. It has some intense units.
Yeah, it does. I missed that. And is that dotted or is that coulombs times meters?
It's coulombs times meters.
Okay. I just want to make sure because it has a little dot in there.
It does, yeah.
I would question the chart. I guess it's not given in this, but the chart. Well, we said the charge of the carbon is neutral, so that.
So when you say charge, you mean the little q?
Yeah.
Yeah.
So then I guess would that be the 6? Because we had the 6 protons.
Yeah. So okay, so that's right. So that's the charge that gets pulled over
Okay.
into your dipole. So I think 6 would be six electrons, leaving 6 protons behind would be a reasonable number. You could also imagine a situation where 1 electron gets pulled over, leaving 1 proton behind. Ultimately, that's what the polarizability is about. The polarizability is actually saying we actually don't know how much charge gets pulled over how far. What we can measure more easily is the product of the charge and the distance. That's why in the numerator for the polarizability, it's coulombs times meters. So that quantity right there is Q times S. Q, the charge that gets pulled over, and S, the distance between them. But I think it's tough to think about the polarizability here. I think an easier way to think about this problem is to pick an amount of charge that does get pulled over, like 6 electrons, for example.
Okay. So then we can say negative Q equals the negative. It would just be negative 6e, right?
Yeah. Oh, it actually, yeah, that's right. Yep. Yeah.
Or you can just do E. I guess you don't even have to worry about the 6, or does the 6?
No, E is good because it says the charge of the electron, and it's definitely not negative 6 coulombs.
Okay. That's
Okay.
kind of where I'm at.
Okay, this is good so far. So let's go through a few other quantities. So how about M? Do we have M?
Yes, because the mass of the atomic mass of 12.
Yeah. So tell me what that M is. Is that an electron? Is it the wire? Is it what's the thing that's moving?
Well, it's the speck of coal, so it's the carbon.
Yeah, okay. So
atom.
It's the entire carbon atom that's moving. Great.
Yeah.
Yeah. And you're exactly right. Atomic mass of 12, we can convert into kilograms. So you could say like M equals 12 AMU equals somehow we convert that into kilograms. It's a bit of a mess to convert it into kilograms, although that is the correct way to do it. I'm sure we can find a conversion factor, right? Because that means that's the official correct way to do it. The other thing, and we can look up a conversion factor between AMU and kilograms. The other way to do this is that you can say, look, the carbon is made up of 6 protons and 6 neutrons and 6 electrons. 6 electrons basically weigh 0 in comparison to protons and neutrons. And so therefore, you can say that carbon is approximately 12 times the mass of the proton. And that's how the book does it in their solution. So that's a bit of a cheat, and it's not fully accurate. So the atomic physicists and the nuclear physicists will come hounding you down, but practically speaking, it's essentially the same number. So that's another option, is to say that the mass is 12 times the mass of a proton. And the mass of the proton you can also look up in kilograms.
Gotcha. Well, I looked this up the other day because I was I thought I'd gotten quite a ways on it, and it was I think 199 e to the negative 20.
That seems like the right order of magnitude to me about. Okay. Okay. So excellent. So we have all these numbers. So it seems to me like at this point, the main thing that we're missing is E minus and E plus. So let's start with what is the equation for the electric field due to a wire?
That one is I feel like it was lambda equals Q divided by L. No, that's the charge density.
That is the charge density that appears in the equation for the electric field due to a wire.
Oh, it's
Rudra.
K times lambda over. Oh, what is it? Over. I have to see if I have it
What's
right
up?
here.
Well, I was going to ask, do you have the equation sheet of
I
common
can pull
charge
it up.
distributions? Yeah,
Yeah,
maybe if you could do that, and then just so we can have it on video, highlighting the.
Yeah, for sure. So yeah, let me just find this real quick and share my
Oh, I have
screen.
K times lambda over R, which in our case R would be D, correct? D minus. This.
Yeah, you're off by one small constant. Yeah. Okay. So which one is this? Yeah. All right. So this is an infinitely long wire, which we do not have. We have a finite wire, but we should use the simplest equation that we can start with for this problem, in my opinion. So yeah, so this one is the one. And so this we've got 1 over 2 pi epsilon. There's your lambda, which is, like you said, it's the linear charge density. So that's Q over L. And then 1 over 2 pi epsilon naught. So K is 1 over 4 pi epsilon naught.
Oh, okay.
So I think that the equation that you're looking for is 2K lambda over R, where R is the distance, the shortest distance to the wire from a location.
That makes sense. Yeah, I have it written down. It's not all together. So obviously my thoughts weren't totally coherent.
Okay. Okay. But so that's the equation that we need to use. So that kind of tells us what we need to stick in for our E. Yeah. Excellent. So let's just write that equation down just so that we have that somewhere so we can refer back to it. Well, can we just write down like E due to a long wire equals?
Yeah.
And then we can figure out what E plus and E minus is specifically.
Let me move this real quick.
I have a quick question.
Yeah.
So I noticed how when we were deriving the formula, like, for the acceleration, I noticed we're not using vector notation. And is that because we know this is going to be in the x direction and we sort of are just figured out the signs instead?
Yeah.
Okay. I just wanted to make sure.
Yeah, that's exactly right. But you are absolutely correct, Rudra. Right. These are vectors. And so to be fully accurate, it would be good to use vector notation here. I will say that the point of this problem is less the vectors and more thinking about the polarization of the atom and thinking about the effect that a non-uniform electric field has on that polarization is the main thing that they're driving at here. So that's the only reason. I mean, you know me, I'm like a huge vector hound. So so what I would love to do is but then you have to, okay, well that works actually. Then you get a vector for your acceleration. That's also a vector. Your A and the MA.
Cool. Yeah, I just wanted to make sure that that I knew the reason why we didn't need it. I just wanted to sort of kind of make sure that the only reason we're not putting it is because we know it's in the X direction.
Yeah, that's right.
Okay.
That's exactly right. Yeah. And so then when you're writing this, so again, let's just put the E due to a
Oh,
long
yeah.
wire period. And then we can say E plus equals.
And that would just be like a D, right? Or an R, I guess.
I think R is, yeah. And then really, right. So to properly do this equation, then you would want to define like R is the shortest distance to the wire, and K is this value, 9e to the 9 Newton Coulomb squared per meter squared. And lambda is Q over L. This is thank you. This is I appreciate this. This is very it's important, right? Like what do these quantities mean? Because that's how you have to know that to be able to apply it to the problem.
To the wire or to the from the wire to wherever you're, I guess, to your atom.
Either is the same because R is a magnitude, so
Okay.
it doesn't have a direction. But you're right. R hat is the vector that points. This is the shortest vector from the wire to the. Oh, but vectors don't have. It's the vector with the smallest magnitude that points from the wire to the charge. So here, I would say we can replace that R hat with a slightly more specific X hat. Yeah.
Makes sense. Okay.
Yeah. Okay, and we have the lambda. So now I think that you're exactly right. That distance R is exactly what we need to figure out for our E plus and our E minus. Okay, which is what you were trying to do in the first place. So sorry for slowing you down.
Oh, you're fine. No, you're fine. I just I think part of my biggest problem with this is starting to get all the different stuff combined. So basically where I was going with the E minus equals the 2k lambda over d minus, and then I was saying half of that because we're going to the center. So would it just be like the s over 2?
Yeah.
Half the size of it.
Yeah. So can we put S on the diagram that you have above? Because I think I agree with you, and that agrees with the notation that the book uses. Yeah. Okay. So the total. So I think yeah.
Oh.
I think actually those distances are S over 2, right? So I think the total distance between the negative and the positive and maybe you can just indicate that total distance is S. Yeah.
That makes sense. Yeah.
Yeah.
I don't know why I was doing it the other way. And I think it's for E plus, then it's basically the same, except for you do D plus S over 2.
Mm-hmm.
And that's kind of where, and then you just plug it in.
Right. Right. Okay. And so you plug that in, and now we have everything except if we plug that in, right? The things that were not explicitly given are the Q and the S.
Mm-hmm.
Those are the problems. And so then we kind of have to ask ourselves, okay, well, like how do we manage those? And that's where the polarizability comes in, because the polarizability is alpha. Let's see. So alpha times the relationship there is alpha times the electric field is equal to Q times S.
Okay, so you said alpha times E
Hmm.
equals Q times S.
Yeah.
Okay, so we have E, we have, so then that gives us the value of Q and S, but oh, and we said Q is that, so then, okay.
Yeah. So, right. So if you said Q was 6E, so we would plug that in. And then if we know alpha and we get E, then we could solve for S if we wanted to.
That's what right?
Right. And now what value would you use for E? Because, right, the whole point is that it varies across this thing.
Well, you have, so you KQ over L.
Over what distance would you use for the electric field?
Would it be L or D?
It would be D. L only factors in for the charge density part of it.
Oh, okay, okay.
But the thing that you're dividing by is like the distance from the wire.
Oh, okay. Yeah, that makes sense.
Okay. So now, okay, so let's actually write that in with your S equals, because at that point, then I think between all of these equations, we actually have an A equals where we know all of the quantities.
So I'm gonna move this real quick to try and make it a little more organized. And then you said, what was that you just said I missed?
All right. So if you put in your quantity, like how would you calculate E? If you
Oh,
put that in, then you've got everything. You've got S, which you can plug into your E plus and your E minus, which you can then plug into your A. And so then you've got everything in terms of quantities that are given. Yeah, 2 KQ over D, I think.
oh, because that's
I think, yeah, and I think you also need an L in the new denominator.
on.
On the 2KQ over D. Yeah, because the Q over L is the lambda.
Oh, yeah. Okay. Yeah, because lambda equals Q over L.
Yeah.
And then that equals S, we said, right?
That's right.
So now we have A equals okay, we went here. And then we were just solving for S, so then S, okay, that goes where, I think this is where I start getting a little.
Yeah, right. This is crazy. Just use S as a variable, right? Say, okay, I'm going to calculate S and then plug it in separately.
Okay.
Because otherwise you're going to have fractions within fractions.
Within fractions.
Yeah.
over.
Yeah.
Okay.
And now if you calculate S, you can plug it into that equation. And you will get an acceleration. And then you can answer the second question by doubling all of your distances.
So
tripling all of your distances.
On yours it's tripling, and then I don't know what I have. If I have, it's the same no matter what you do. So you just do that, and then you have your new acceleration divided by your old acceleration is supposed to give you the answer to that one, correct? Or do you just triple all of them and that's your answer?
No, you're right. It's asking for the ratio. It's asking for A when you're 3 times further away divided by A times when you're this distance away.
Okay. And then essentially for the equation that it's asking for, we would have to go ahead and put the S equation in and just simplify everything. Is that correct?
Yeah, that's right. So that's what I would say. This is the so that is the like formal way and the fully correct way to solve this problem. The problem that you're going to run into with this, and but this is like if I had my way, like they would accept this as an answer, right? Because really you've got this idea of your force plus your other force divided by your mass, that's your acceleration. Now the problem with this is that you've got two numbers, right? So your quantity d minus s over 2, what you're going to find is that s is an incredibly small number. Like if you look at your alpha, if you scroll up a little bit here, your alpha is 2 times 10 to the negative 40. And s is proportional to that.
Yeah.
Right. And q is small. Q is 10 to the negative 19. And 2kq over dl will be something, k is 10 to the 9. So it's but q is also, but q kind of balances that 10 to the 9 out because you've got that 0.7 times 10 to the negative 7. So you're going to end up with something that's like 10 to the negative 20 meters.
Okay.
So then you've got d, which is meters, minus 10 to the negative 20 meters in the denominator over here. And you've got d plus 10 to the negative 20 meters over here. And you're asking a calculator to tell the difference between those two numbers. And that is where calculators kind of start falling down. Like, yes. Yeah. So
I'm learning about that numerical analysis right now, why they do
that. Yes, that's exactly right. So that's what makes this problem tricky, in my opinion, is like this part. I mean, I don't mean to say that this is trivial, right? But this idea of, the atom polarizes, it stretches out a little bit, it feels a different electric field on its positive end than its negative end, and therefore it feels a net force. Like that part is good. But then what you have to figure out is, now you've done this, how do you actually calculate it? Like on a calculator without your calculator giving you a totally bogus answer because you're running into round off error. So that's where that when they talk about the binomial expansion, that's what they're talking about. Is what we can do is we can express this in a better way so that it's more numerically stable. So that's kind of the point of this.
Okay, and I think so. Getting to this part wasn't I was at.
Yeah.
And to be totally honest with you, I think the binomial expansion is what's giving me issues because I've been out of school for a little bit.
Yeah.
I come back into 2 doozies of class.
Yeah. So let's do the binomial expansion part of this. So what I would say is this right here. This right here is our shining equation right here. Okay, and we've got that part. So let's think about the binomial expansion. So what I would say is, so that's our shining equation. Let's do A equals, let's factor out all of the common stuff, and then we can focus on the remainder and we can talk about how to get that into a more numerically stable form.
Okay. Actually, can we just do it in the general, or no, I guess leave it there.
Great. And I would also say you've got to divide it by m.
Oh yeah.
Okay, great. I'm gonna fuss with this if that's okay with you. Okay. Sorry, I'm trying to.
Oh yeah. I didn't even think about that. I could have made it easier.
That's fine. Okay, and then let's see. Is my pen letting me draw? No, it's not. Okay. Ah. Okay, and then we just need like a division symbol. It needs to be like -2 or -q 2k lambda. Is this a minus sign right here?
Yes. That one?
Yeah.
No, that one was a positive.
Yeah, but you factor it out. If you factor out -q,
Oh yeah, it needs to be a yep.
which I only did because yeah, I was changing it. So you were right
Oh, makes sense.
initially, just to be clear. Yeah, great. And then if we divide by m in that front fraction, then we have something. Okay, and this is starting to look to me like something I would target. This thing right here. This is the kind of thing that I would target as potential for the binomial expansion. Okay, so this is so Michael and Rudra, like I haven't let you guys get a word in edgewise. Do you have thoughts on how to expand this or how to adjust this?
No, not really.
So what I'm thinking here is we find a common denominator and go from there, and keep simplifying until we have I think one expression.
Oh, okay. Yeah, okay. So yeah, so you can definitely, right, you can do like the thing where you multiply both sides by the opposite. Yeah. Yeah, that totally works. Um, okay. Could I show you guys my cheat method?
Yes, please.
Okay.
Please.
Okay. So here what we have is basically what I want to do it, and the book tells you to use a binomial expansion. I am not a fan of telling anyone to use the binomial expansion because as they say here, let me zoom in on this, right? The binomial expansion is exactly this. It's that 1 plus a small number to the n is about 1 plus ne. And that's true, but really the more useful thing is the Taylor expansion. So Amy loves the Taylor expansion. And the binomial expansion is like one small application of it. But the Taylor expansion is more useful. So what I would be inclined to do would be to say, look, what we want to know is S is very small. So the Taylor expansion focuses on approximating complex functions, um, approximating complex functions uh, near a particular point. So I think what we want to do is this is a complex function or a fairly complex function, and we want to approximate it near the point s equals 0. Does that sound kind of reasonable to you guys?
Yes.
Okay. All right. So if that's what we want to do, then that's the major part of the battle. What function do we want to approximate, and what around what do we want to approximate it? So then let's see if Wolfram alpha will help us out. Okay, so we have 1 over d minus s over 2 minus 1 over d plus s over 2 expand try near s equals 0. Yes. Okay. All right. So if I ask Wolfram Alpha to do something that's too hard and it takes too long, it'll quit on me. And then I have to use my actual Mathematica installation instead. But what this is telling me is that it's taking this function and it's expanding it around s equals 0. And this, it says, is what a good expansion is. And so instead of using this complex expression, I can just write instead of it s over d squared. And that's what Wolfram Alpha claims I can do.
How is that accomplished?
Yeah, so what it's using here is the Taylor expansion. And the Taylor expansion is, let me just pull it up here. So what it does is it goes through this. This right here is the formula. So the Taylor expansion is a theorem really that says that you can approximate any function around a point A with this series. So what this is the nth derivative of the function of my complex function evaluated at A divided by n factorial times the polynomial x minus a to the n. And so what Wolfram Alpha is doing for me is it's taking the derivatives of my complex function and evaluating them at s equals 0, and then dividing by n factorial, and then multiplying by x minus a to the n, and x minus s to the n.
Wow.
Okay, and so you're approximating that expression by using the Taylor expansion?
That's correct. And the reason that I say the Taylor series is so much more powerful is because it works for any function. It works for any complex function. Whereas the binomial theorem only works for functions of the form 1 plus a small number to the n. And so this is just much more powerful. And like, actually, you can, what I want to do is play these videos, right? But like this video on the Taylor series is just absolutely amazing. It shows you, maybe we could just take a peek at it. I don't know. Do you guys have a little bit of time to?
Yeah.
When I first learned about Taylor series, I definitely didn't appreciate just how important they are. But time and time again, they come up in math and physics and many fields of engineering because they're one of the most powerful tools that math has to offer for approximating functions. This class was not in a calculus class, but a physics class. We were studying a certain problem that had to do with the potential energy of a pendulum. And for that, you need an expression for how high the weight of the pendulum is above its lowest point. And when you work that out, it comes out to be proportional to 1 minus the cosine of the angle between the pendulum and the vertical. Now, the specifics of the problem we were trying to solve are beyond the point here, but what I'll say is that this cosine function made the problem awkward and unwieldy, and it made it less clear how pendulums relate to other oscillating phenomena. But if you approximate cosine of theta as 1 minus theta squared over 2, of all things, everything just fell into place much more easily. If you've never seen anything like this before, an approximation like that might seem completely out of left field. I mean, if you graph cosine of theta along with this function, 1 minus theta squared over 2, they seem rather close to each other, at least for small angles near 0. But how would you even think to make this approximation? And how would you find that particular quadratic? The study of Taylor series is largely about taking non-polynomial functions and finding polynomials that approximate them near some input. The motive here is that polynomials tend to be much easier to deal with than other functions. They're easier to compute, easier to take derivatives, easier.
Yeah, so for us, the thing that's really important is easier to compute.
Great, just all around more friendly. So let's take a look at that function, cosine of x, and really take a moment to think about how you might construct a quadratic approximation near x equals 0. That is, among all of the possible polynomials that look like c0 plus c1 times x plus c2 times x squared for some choice of these constants, c0, c1, and c2, find the one that most resembles cosine of x near x equals 0. This graph kind of spoons with the graph of cosine x at that point.
Okay, so I don't, but I'll put a link. I'll put a link to this in the chat of the, or like in the description of this, so that you guys can watch this if you're interested in finding out more. But this is fundamentally like what's going on with Taylor series is you're finding this polynomial approximation, and it turns out that there's a very direct formula for that, and that's what Mathematica is evaluating for you. Is it's taking all the derivatives that you need to evaluate that formula. So what I'm saying here is that this, if we look at this, so then all of this is to say that this entire expression right here, this entire expression can be replaced with s over d squared.
Is there a way that we can tell what the margin of error is going to be with the approximation?
That's a great question. That is a whole field of study. I'll let TJ comment on that, since he's taking numerical analysis.
About that. That is, yeah, that's you can calculate it. It just takes there's several different ways.
Well, I mean, is there a way to tell if, because in this problem, we're calculating the difference between s over 2 difference in charge placement. And so we're doing an approximation. How do we know that this approximation is going to be accurate enough to show the difference in electric potential?
Yeah. So I agree. TJ is absolutely correct. There's a lot of different ways to calculate error. One of the simplest ways to calculate error is to estimate it as being the term after your terminal thing, right? So if I'm saying s over d squared, an estimate of the error would be s cubed over 4d to the 4th. And it's not the exact error, but often it's the easiest way to estimate the error. And it does usually give you a rough, especially for series that are strictly increasing like this. It does usually give you a rough.
Okay.
It'll give you the right order of magnitude for the error. So what you could do is you could look at that and sort of, evaluate that and decide whether or not you want to go more precise and include that term, in which case s to the 5th over 16d to the 6th would be an estimate of your error.
Also, just a quick question. That plus o s to the power 7, so that's the order of the approximation?
Yes, that's right.
Okay, so this entire approximation is to the 7th order.
That's right. So they're giving you the polynomial terms up to the 7th order.
Oh, okay. And they're essentially like cutting it off, like truncating it right over there.
That's right. You know, and it usually makes sense to truncate at some point because you're saying S is small.
Right.
And so S to the cubed will be really small, and S to the fifth will be insanely small, and S to the seventh, who even cares? And
So
it
we
just
can
kind of,
use as much of the approximation as we find necessary.
yes, that's
And
right.
this is describing that up to the 7th power.
That's right. So if you look at these cool, what I love is he does these, let's see if I can find one where he kind of goes through and he does the successive approximations. So you can see them get more, yeah, okay, let's look at this one. You can see them get more and more accurate. Right, okay, so this approximation is the linear approximation. And you can see it's actually pretty good right around 0. Do you see what I'm talking about there?
Mm-hmm.
Yeah. So like really, you know, so it kind of just depends on what kind of accuracy you need and how close you are to 0. You know, if you're over here, then this is clearly a terrible. If you're over at x equals pi, this is a very bad approximation. But if you're at x equals like 0.00000001, like probably linear is fine. And when you think about the computing power required to do a linear, you know, x times a number plus another number on a computer compared to the computing power required to do out to 3 to 7 orders of magnitude, it's enormous. So that's one of the reasons that approximations are so critical. But you can see as he goes on, it'll get better and better.
The next term ensures that the rate at which the slope changes is the same at that point, and so on, depending on how many terms you want. The more terms you choose, the closer the approximation, but the trade-off is that the polynomial you'd get would be more complicated. To make things even more general, if you wanted to approximate near some input other than 0, which we'll call a, you would write this polynomial in terms of powers of x minus a, and you would evaluate all the derivatives of f at that input, a. This is what Taylor polynomials look like in their fullest generality. The value of a changes where this approximation is hugging the original function, where its higher order derivatives will be equal to those of the original function.
This is a really good video.
This is my favorite math guy.
Yeah, it's just the animations are just fantastic. But yeah, so all of that is to say that S is small, so we want this to hug our original function about S equals 0. And then let's see. So TJ, let's get you that expression. So you can replace that entire expression with S over D squared. That's the claim. Yeah. And okay, and so then actually also what's interesting is see how in the numerator you now have Q times S?
Yes.
So you could replace that with alpha times E. And then you never need to actually calculate S separately if you don't want to.
That entire bracketed term gets going down to S over T squared.
That's right. This whole term right here turns into this term. And what I'd like to do is maybe highlight it. Maybe I can do that. Okay, let me.
And that was just a regular expand in Wolfram?
Yes.
Not like a specific Taylor expand?
No, that's right. So that's the beauty of the Taylor expansion is that it's just this kind of general thing, right? So the syntax for that in Wolfram Alpha is expand and then function, and then near, and then you tell it where you want your approximation to be good at.
I'm not even sure you have to put expand in there.
You might be right about that.
It limits how much information it gives you, but it'll be in here if you even just put the.
Oh, wow.
Yeah, it's right there. Yeah. If you put near something, it's gonna give you the expansion of it.
That's cool.
Yeah. So Rudra, I would say that if I were doing this by hand, I would do exactly what you suggested. I would start out by simplifying my fraction so that I only had to do right? Because the Taylor approximation requires you to do derivatives of your function. And if you have two separate fractions, then you're going to have to, that's like extra. I would try to simplify my function as much as possible so that my derivatives were easier for doing the Taylor expansion. So I would absolutely start with that step. But, you know, but what I always tell my physics students is do it by hand and also do it on Wolfram Alpha. And if you're not a physics major, you know, I don't know. This is like critical to physics. It's maybe critical to some other areas. I don't really know how much, like in physics, you have to know this and you have to be able to do it by hand and do it quickly. I'm not sure how much that's true in other disciplines. But you definitely want to know the idea and like how to ask a program or a mathematician to do it for you.
Could you tell me again what the Taylor series was, the equation?
Yes. This is exactly how I would write it. I would put an f of x equals up front.
Equation is brilliant.
Yeah. Yeah, it's amazing.
I'm having issues with one right now. I was actually going to ask you about after we get done if you had a second, if you had any ideas.
Is this part of differential equations that you get this? Or
no, actually, this is typically calculus 2.
Two, yeah.
I should already know this then.
But it's not necessarily strongly emphasized. I mean, it's like one theorem of many.
Series.
Yes.
I'm pretty sure we did one example at least of this. But I didn't know what exactly it was doing.
Right. Or why it's so useful.
Yeah, like physically, what exactly it was going on. It's like, okay, this is another series. That's cool.
Yeah. Yeah, super powerful.
It's a big shortcut.
Yeah, it's enormous. And so, oh, sorry, I didn't need to stop the share. So on the one hand, this problem that I give you guys is an absolute monster. And like, I shouldn't ask you to do it. But on the other hand, it's one of the few problems where this is really needed, right? And it's really neat. It's really important in this case because S is so small, you really will truly run into computational difficulties. So I really like it because it's really well motivated. And it really is something that as a physicist, like I've had to do this before. I've had one number minus another number, and they're both nearly identical. And I run into trouble with machine precision. And in that case, I look at the thing and I think, you know, how can I rewrite this so that I can calculate it more accurately? So anyway, so for those reasons, I really like the problem, but it's a lot to put into one problem.
Mm-hmm. That's okay. Challenge accepted.
So my question is, so that equation that it accepts as the answer, I feel is different than this.
Oh yeah. Okay. Right. So now let's write. Okay. So yes, now this kind of comes to this question of like this equation that they use is different than this. So let's write it in terms of the first thing that we need to do is expand that E.
Okay. That's probably where it's. Actually, I'm going to write it different. It's over D, correct?
Yeah, over d times L, right? Because you're trying to do KQ over KQ, sorry, K lambda over D is what you're trying to do.
Isn't there a Q in here for the E? Or is that?
Yeah, that's right. That's right. But it's really 2KQ over lambda. Sorry, 2K lambda over the distance. So lambda is not just Q, it's Q over L.
Oh yeah, okay.
Okay, and I think you've dropped a 2.
Yes, I did.
Yeah, perfect. Okay. And I would also suggest changing that lambda into a Q over L. Okay, so let's group terms and simplify the fractions.
Okay, so we have 4K. Is that right, or did I add an extra 2 in there?
Nope, you got both the 2's.
Okay. Q squared over D. L squared.
Good. I think maybe you have a K squared, not just K.
Oh yeah.
Okay.
Yeah, that's there,
Great.
that's there, that's there, that's there.
Yeah. Okay. So now can you simplify that to like a numerator divided by a denominator?
Yes. Okay, so we'll have
Yeah.
I think that's it.
That is. And even so, the book won't the problem won't will still give you trouble because it doesn't like the K. So you'll need to turn that into 1 over 4 pi epsilon naught squared. It's just really, but there it is. 1 over 4 pi epsilon naught, there's the squared. And there's your 4, Q squared alpha M L squared D cubed. Yeah.
I think I got it all.
Yep.
Okay.
Also, the only thing that I was gonna say is like I think we're taking the magnitude of the acceleration, so I think it like becomes positive.
Yeah, that's an excellent point. You've got this negative
Gotcha.
sign here, right? And that's correct because the acceleration is in the negative x direction.
So we can just do the absolute.
Yeah.
Okay.
Or I think the way that I would write this is I would take away these absolute signs and take away this negative. And then draw your absolute signs here, right? So this is our acceleration. So therefore we're going to take the absolute value of this thing and that turns into positive.
That Taylor expansion worked out really well.
Yeah. And don't forget to draw your absolute value signs here. No, not there.
Oh,
That's because
yeah.
you've already taken the absolute value of that. And all of
That's
those
right.
quantities are positive. Yes. Yes. I have no complaints about this notation. Yeah, the Taylor expansion dramatically simplifies it.
That was a pretty neat thing.
And there you are.
I was like halfway, a little over halfway there, and just at the point of the Taylor expansion is kind of where I got off at.
Yeah. No,
Trying to-
I think.
Oh, sorry.
Yeah, no, that makes sense.
Because I was trying to do it by hand and trying to remember how to do it. Because I looked it up on Wolfram Alpha, but most of the time when I look something up on there, I try and figure out or try and make sure I know how to do it at least. And they don't give you the step-by-step on expansions.
Right. Right, exactly. So I'll add that note in here. No. No, okay, that'll play it inside there. Maybe I won't include the quotes. That'll probably make it. Okay, so we did 1 over d minus s over 2 minus 1 over d plus s over 2. Okay. And that's it. Congratulations, you are all physicists now.
Woo!
Particle physics, yay.
That's right. All right, I think we're good to stop recording. Anyone have any final comments on this one?
It's a lot of algebra.